I got this book, interesting book, Dava Sobel. You may know her. She's written about longitude. I think she's got some ties with University of Chicago, but she's written that and Galileo's Daughter, if you know that book too. So she's a science writer and gets very lyrical and poetical and so on in her writing, and it's motivating. And I won't approach her uh, talents. But very interesting talking about and listening about and getting in more. I know probably the last time there was much talk about planets when I was in any kind of school was, the old fourth grade thing when you learn the planets in the order and you learn things about them. There's not much that reaches out to us and talks to us about the planets. Every once in a while, there's a flurry of things in terms of the Mars rovers and different things that have gone there, and we'll talk a bit about that. And we did talk about Perseverance and Curiosity, the rover and the helicopter that were on Mars a few Science Sundays a few years ago in Science Sunday. But I thought just the amount of knowledge that's come out and the breadth of knowledge that's come out about the planets um, it's just phenomenal. There have been over 50 missions, flybys or landings or whatever, just of Mars alone. And it's the easiest one to get to, and we'll talk about a little bit about that too. But just the amount of knowledge that we've gained about these planets, and they're not these nebulous things sitting there. We know about them. We know about their moons. We know about their construction, their chemistry, so much about them. And hopefully, some of this is new to you, gets passed on, and it's not kind of the stuff we learned in fourth grade or so. So much has been learned about the planet since our school days. Advancements in rocketry, computers, analysis, and chemistry, along with many other scientific leaps, have added exponentially to our knowledge of the solar system and the planets that make it up. An hour of time is nowhere near enough to discuss it all, and I'm not knowledgeable enough to cover it all in a cogent way like that. But I can't cover every topic possible. But hopefully, you can gain knowledge and some appreciation for the wanderers of our system, the planets. I'll concentrate on the rocky planets today. I first thought I'd talk about planets, and I realized you can't cover all that. So I broke it up at least into the rocky planets. When I started talking about the rocky planets, I said maybe I should just talk about maybe two of them, and maybe that's all we'll get to here today. But if it is, that's so be it. All right. So I plan to talk about the balance of them in 2 weeks. I'll be doing Science Sunday 2 weeks from now, too. So, what are the rocky planets? What do they have in common, and what's special about each? The solar system formed almost 5 billion years ago. This is a artist's depiction of what part of it looked like at certain points of time. They're talking about different areas of congregation and what materials can congregate in different parts of the solar system based on gravity and speed of rotation and a lot of things. It was a large spinning disk of gas and dust that consolidated over the course of really just a few million years. Most of the gas accretes into the star at the center of the system, while solid material slowly coalesces into asteroids, comets, planets, and more. Things in our system, the cluster of the closest four planets are metallic and rocky. The outer four are gas and ice giants that we'll discuss at another time. But you can see they talk about this the soot line and the frost line, depending upon temperatures and compositions and gravity and so on, and um, and what those are. How, I had PAHs and now I'm not remembering it right now, but basically it's stuff that's associated with life, um, hydrocarbons and polyamino hydrocarbons, I think, allowing forming planets to include condensed carbon compounds. So only certain areas really allow carbon into that area. Inside of the soot line, only metals and minerals condense into planets in that area. So just by physics and geometry and so on, different things can accrete and coalesce in different areas. It's developed a lot by the gravity and the speed of the spinning, calls out what can go into different areas. In the nebula, 98% of it's hydrogen and helium, which don't condense at all. So the closest planet to the sun is Mercury. It's the smallest of the 8 and the fastest going around. It has a very elliptical orbit and averages 36 million miles from the sun, but is often much closer in and often much farther out. You can go out to about 54 million and into 36. Sometimes it's actually farther away from the sun, or to 25 maybe. Sometimes it's further away from the sun than Venus is at the outside of its orbit. Would you think that it travels slowly or quickly when it's in there close to the sun? It's got to go fast, right, to keep its centrifugal force, keeping it spinning and not being sucked in. To counteract the sun's gravity, Mercury must travel very fast. It completes a full rotation of the sun in only 88 days. That speed has had an impact on Mercury's rotation. It's going so fast that it can't keep a rotation up. It's fighting solar wind and different things coming off the sun. So that means it turns on its axis in 59 Earth days. One rotation around in 59 Earth days, 2 months, right? When you think of that, it goes around the whole sun in 88 days, and 59 is roughly 2/3 of 88. So that means it turns on its axis only 3 times in the time it takes to go twice around the sun. So the face of Mercury that's facing the sun stays facing it for quite a while, right? Years go by quickly on Mercury, but days are interminable. Yeah, very much heat. It's so close to the sun, it's gaining a lot of heat. What? It's a sidereal day. Yeah, as I understand it, when we're talking, most of what I'm doing is I'm comparing it to Earth.
Right.
So I'm giving you a frame of reference or things that you can put in your frame of reference to understand the speed that it travels in. You can make it around the whole transit of the sun or revolution around the sun in 88 days.
Mhm.
But in that time, it only turns about 1.5 times around on its axis. Okay.
Yeah.
So
Okay. Yeah. Yeah. Should I say what the difference is between a sidereal and a solar day?
yes,
So a sidereal day is the time it takes to turn 360 degrees, right? But if it's going around the sun, that's, and you turn 360 degrees, the side that's facing the sun when it finishes that 360 degrees might be facing away from the sun or not, depending on how far it's gone around in its orbit. So a solar day is how long it takes for, like, you're standing on the surface and the sun's directly overhead, how long it takes for it to turn around and the sun to be directly overhead again, which would be more than 360 degrees, right?
because you've moved in that time.
Because you've gone around, so you have to turn further to be facing the sun again,
Right.
right?
Yeah.
And is it 2-to-1? Is it exact?
It's 3-2.
For the sidereal, but for a solar to be facing the sun again, is it? I think. And never mind.
Yeah.
Yeah.
So its sidereal year is 88 Earth days. If that, and I may be jumping off what scientists really want to say about it, but I'm trying to say in here that it takes in 88 Earth days, it'll go around the whole sun. It'll make its trip around the sun. And its Earth day is actually 58.65. And if you do the math, it comes so close, almost mathematically perfect to 3-2. Okay. So why that geometry comes out just that right, why the numbers come out just that right, it's hard to say. Um, Moons and Earth and planets slow down and speed up. Is it just 3-2 right now for some reason, you know? Right, yeah, yeah. So, um, yeah, when you think of it, and if you try to put in your mind a daybreak on Mercury, if you'd be there and you'd see it, and it would actually be, days later that you just start seeing morning coming, right? And noon would be, um, you know, 20 days later, right? So that sun is just staying there in the sky, staying in that place right there for quite a while. It's not changing like we're used to the day changes.
So they don't have daylight savings time.
They don't need daylight savings time, man. Yeah. They are saving a lot of daylight already. So, two more facts concerning Mercury, and then we'll discuss how this affects Mercury. One is Mercury is one of the most impacted planets in our system. I call it the battered planet. And this kind of shows not as much as some do, but if you look at some pictures of Mercury, it has been battered by asteroids and comets and collisions from space matter, for its whole existence for 4 billion years. And you see amazing amounts of collision evidence all over it. Okay, thousands of impact craters are all over the planet. Also, Mercury stands very erect. Its axis is tipped only about 3 degrees relative to the sun, so it's very erect. So, how does the sun impact Mercury, do you think? You'd have to talk about it. What? Very hot. What's that? It cooks it, right? Yeah, it has very little atmosphere. The sun is very bright. There's a lot of solar wind. It doesn't have much of a magnetosphere to protect it from the solar wind like the Earth does. So all these things impact that it's very hot when it's facing the sun, right? But then, just like there's dawn forever on the sun, there's also nightfall and nighttime forever. I'm sorry, on Mercury, there's always nightfall forever on Mercury as well too. When it turns away from the sun, it's going to not face that part of the planet is not going to face the sun for months, right? And in that time, it gets very, very cold. It has the most change, the highest gradient of temperature change of any of the planets. Okay. So, do you think there'd be snow or ice on Mercury? Not much water, right? A lot would be cooked away, the atmosphere. Actually, because what I said earlier, the tilt of only 3 degrees of the axis means that parts of the north pole of Mercury and the south pole of Mercury are really not facing the sun at all, right? So these big impact craters and the development, the deep areas in that area, in the last few years, they've discovered pockets of ice hidden deep down at the north and south pole that have been there for many, many hundreds of millions, billions of years. Unable, probably deposited there by comets hitting up there, but the sun never hits in that area, and so it doesn't boil it away. All right. So very amazing changes, gradients of temperature on the planet of Mercury. I put a few other. Scott was having trouble with this, I saw too. Yeah. A highly elliptical orbit, most elliptical of all the planets. Its diameter is about 38% of Earth's, 3,000 miles across. It's the smallest planet now that we've kicked that Pluto out of the club. Very metallic, high in metals. Actually, there's some thoughts about Mercury, in which its core is sizable, maybe like 80% of the planet, 70 to 80% of the planet is its core. And the thought that is the theory that's going around now by some scientists is that it may have been out in a much further orbit years ago, and maybe interacted much more with Earth and with Venus and the other planets, the other asteroids in the belt and things like that too, but may have had a glancing blow, is the thought, from a large planet, bigger than it, that skidded across it, knocked off significant amounts of its crust, and then sent it into this orbit, this highly crazy orbit around the sun, as a much smaller planet, sped it up, and so on. So its core is significant, but it's not an active core like our core on our planet is too. I have some pictures of that we'll show in a bit as well too, or some representations of it. Its density, because it's so metallic, it's the second highest, just barely after Earth. Earth is the most dense of all the planets. Its core is 57% of the Earth's is only 17% of its volume. Heavily cratered, like I said. And this is another interesting aspect of it too. Solar tides. It is so affected by the sun that even though it's a rocky planet, the sun's gravity pulls on it. There's not water to pull like we're used to here, but it actually pulls on the outer surface, and it can pull it up as much as 20 to 40 feet, they're speculating. Immense amounts. And that's, again, that sun is there in that spot, right, high overhead at that spot for quite a while, and the whole planet bulges as it goes around the sun. Amazing amounts of growth and of the crust of it too. So like 20 to 40 feet. Imagine just being there and things going up and down among you. Only 2 exploratory probes have investigated Mercury. Mariner 10 did 3 flybys in 1974 and 1975. I think they mapped something like 40% of the planet. All they could do was fly by. Messenger was designed to actually, Messenger was the next one. It was designed to actually enter Mercury's orbit, which is a really difficult task. Why would it be so hard to get to Mercury? What was that? Right. Yeah. I mean, you're trying to get around the smallest planet in the solar system while you're flying almost directly towards the largest object in the solar system, which has gravity that affects Mercury by 17 times as much as the moon affects us here too. So very difficult to get in. The story is that the amount of fuel you'd need to slow yourself down if you were on a probe is more than the probe could carry, right? It's going so much towards the sun that you'd need to brake it so heavily that that's more fuel than your probe can carry. Another thought about it? Right. Right. Yeah, you have to slow down, he's saying. So actually, I think the name is Bepi Colombo. Bepi was a nickname, an Italian man, and he developed a method by which, a physicist, he developed a method by which you could actually get to Mercury and get into orbit. And it's using the other planets in the solar system, right? So they launched Messenger in, I think, 2004. So they launched the Messenger spacecraft in 2004. It flew once around the Earth to get on a trajectory, did 2 flybys of Venus on its way towards there, did 3 full flybys. Each of these is going around going in an orbit around the sun while it's doing it, right? And it did 3 flybys of Mercury to slow itself down more, and finally entered into orbit something like 7 years later. It took 7 years to get there. When we get on or when we send a probe to Mars, it gets there in 5, 6 months or something like that, because you're not competing with the sun's gravity as you're doing that way. But 7 years to do all this path around. So Mariner had only 3 flybys in the mid-70s, and that's all the knowledge we had of it. This Bepi Colombo developed a complicated plan to allow the probe to actually slow down enough to achieve orbit around Mercury. It took 32 and a half trips around the sun to do this, to slow down enough. 1 flyby of Earth, and it reoriented the messenger spacecraft, and 2 and 3 flybys of the other, and ultimately 4,100 orbits of Mercury over the years of 2004, which took off from Cape Canaveral, to 2015, when the fuel finally exhausted and the probe was directed to crash into the surface of Mercury. So the first 6.5 years were spent in traveling to its rendezvous. In comparison, a rocket can reach Mars in between 5 and 7 months, and the Moon in about 3 days. Mariner completely mapped all of Mercury and found unexpected ice hidden deep in craters at the North Pole that is protected from the boiling sun. Other design intents were to investigate Mercury's high density, geological evolution, magnetic field, its core, and its exosphere. This is a picture of Mercury. It's actually the sun, but if you can see Mercury in there, there's a sunspot that Scott talked about a while back. There's a sunspot, so that's not Mercury. But can you see it? Yeah, right there. It's amazing, huh? Atmosphere, they call it an exosphere, and it's very minimal. Most of the atmosphere is boiled away, knocked away by solar winds. Imagine the solar winds that come off there. If we didn't have a protective magnetosphere around Earth, we wouldn't have all the communication systems we have now. It would get knocked out by this highly charged ions emanating from the sun. So yeah, they don't have that protective stuff. No magnetosphere and very little atmosphere. It has I think it has a magnetosphere that's kind of self-created and self-perpetuated. I think the solar winds penetrate Mercury so much it knocks up some particles, ions and things that help protect it to some extent. So it's a mechanism of its own safety, I guess. But I thought that was an interesting picture to show too. It observed, so Messenger, when it came in there, observed chains of cliffs that are snaking across a brutalized terrain. Over 100 narrow, flat floored troughs at the heart of the Caloris Basin. The Caloris Basin is a feature that's there that is a crater that's 1,800 miles across. An enormous crater there. A lot of things that happen there, the planet has shrunk and expanded because of heat and so on, and as it cooled off from its hot core, it cooled off, and so there's crevices and cracks and things there as well too. But they can start looking at these things and make observations. For example, they've seen volcanic flows on Mercury, right? And you can see craters impeding onto already formed volcanic flows. And you can see volcanic flows that have impeded over craters. So you can start telling a timeline of what happened when on Mercury from the observations of this that's going on. Mercury has not had many volcanic incidents in the last, I think, maybe billion years, something like that, a long time. It was 1,800 kilometers of Caloris Basin, which is about 1,000 miles actually. Wider than Texas, basically, this basin. And it's surrounded by a ring of forbidding mountains that are taller than 4 Empire State Buildings piled one on top of the other. They can start seeing, although erosion doesn't happen very often on a place with no wind and no water really. You can still see settling, and some of these cliffs are very stark and sharp on newer craters, and they've settled down with the solar movement and the solar tides and so on Mercury later. So the probe actually detected evidence of volcanic activity change as recently as 20 million years ago, 20 to 25 million years ago. They found the core of Mercury is much larger than Earth's. It's almost 70% of its volume. Scientists theorize that Mercury, Venus, Earth, and Mars may have all formed in roughly the same area of the solar system and interacted with each other and the other rocky matter circulating around the sun, sometimes pretty violently. A major impact, possibly a glancing blow, knocked Mercury off course and removed most of its crust, sending it into its present very elliptical orbit. So these are some of the probes. Mariner back in the 70s, here on the left, solar panels, and which has since crashed into the system, and Messenger here. Luckily, the 30-year gap between Mariner 10 and Messenger will not be repeated. Actually, Mercury has another visitor on its doorstep. It's called Bepi Colombo, named after the man that figured the path of how to get there. It's a joint venture between the European Space Agency and the Japanese Space Agency. This probe is taking the necessary flybys and is going to enter orbit in December of 2025, so a year from now. It was scheduled to go in a little sooner, and they had a problem with a motor, rocket propulsion activation, so they had to delay it. It'll deploy 2 different probes that will examine Mercury's surface, interior atmosphere, and magnetic field, all building on Messenger and Mariner's legacy. Here's the Bepi Colombo. You can see 3 parts of it here. This is the part made by the Japanese Space Agency, and I think that's going to go and talk more about the atmosphere. It's going to be a high-flying article probe going around and checking the exosphere, they call it, and the different things on space. This is a ceramic shield that protects parts of the workings of it that is going to get kicked off when it gets into orbit. These 2 will separate, and they'll kick off the ceramic shield, and this is the part that's going to transit down low on the planet and go to within, I think, 12 miles of the planet, something like that. What they do when they go around is they go at a speed and an elevation to get as close a view as they can of things, but then that heats it up pretty much, and then it has to go away. Just the heat of the Mercury will heat the probe up so much that it goes out to maybe 1,800 miles or something like that, and then comes back again when it's cooled off. So that's a bit delayed, but it should be getting in about a year from now. So that should have some very interesting statistics it finds out. 7 years of travel, December 2025, and now they delayed it to November 2026 because of that problem with the thruster. The Mercury transfer module is the whole unit. Then the planetary orbiter, which is the backside. This is the planetary orbiter back here, and this is the magnetospheric orbiter that's going to go around and check the exosphere. So, yes. Thank you, Joey.
I'm just thinking before you leave.
Let's not leave Mercury too soon. Right?
Yeah, you mentioned that Mercury's orbit is highly.
Yes.
In other words, the whole thing, rotates. Newtonian physics can't by itself explained it. You need Einstein's general relativity. And that rotation is one of the first tests that Einstein made of his new theory. It's one of the 3 tests of general relativity.
Right. Yeah, Newtonian physics was unable to explain the whole matter. I thought it was more in like the delay, the timing of the transit of Mercury. Is it because the orbit changes that does that, or?
So it's called a precession of the orbit. So if if you draw on if there were no effect, then it would be making an ellipse that stays exactly the same place every time, right? But there are some effects of like the other planet, like Venus, and some other things that will make it precess a little bit, which means like that high point, the apogee, well, not apo, whatever the Greek
High
term
point
for
of the orbit.
Mercury is, the high point of the orbit moves slow, it moves around the sun slowly, right? So that if you do like hundreds of them, it makes this kind of spirograph pattern, right?
Yeah, yeah.
But the amount that it shifts is a little bit bigger than predicted just by Newtonian mechanics. But if you include general relativity and the curvature of space-time due to the mass of the sun, then that makes up for that. That explains that
That
little extra
explains it.
bit.
Yeah, yeah. Interesting. Yeah, I know. I was looking into some of that, and they were the precessions of Mercury. They happen like about 7 years apart, and then they don't happen for almost another century. And that's how the transits, I guess, that we can see from the sun. And some of those transits were more used to do some proofs of. I think James Cook was sent that was proving where. Now I'm off base on it. It has nothing to do with the precessions.
So it was an observation of the transit of Venus that showed like, because one of the other effects is that mass, gravity, massive objects bend light.
Right.
And so that was observed by, I'm pretty sure it was the transit of Venus. The apparent position of Venus is shifted slightly as it comes in line with the sun from our perspective. So,
Right. Yeah. Yeah. Which is a difficult thing. To measure exactly, before they had chronometers, and when does actually, I think they were looking for 4 specific points when Venus first touched the sun's circular point there, and when it was fully engulfed in it, and then when it was ready to leave, and when it was fully left, and just getting those points was very difficult measurements, and so on. It's amazing that this is more with the Neptune and Uranus, but as they were looking, they had plans for. They understood the orbit of Uranus, but it wasn't following precisely what they planned, and this is in the 1800s, and they didn't see the Uranus wasn't going in the orbit that it should have when they finally located it, and that led them to do calculations that proved that there was another planet out there, Neptune, that was impacting it slightly, and then they knew where to look for Uranus. When it's just amazing the math that can get done at that time. With I don't even know if slide rules were around at that time, but just what they could do with that stuff. So yeah, fascinating stuff, and this is a kind of a flyby of Mercury we're doing here today, but hopefully it gives you some interesting input about what's there. Venus was thought for many years to be a sister planet to us, right? They thought it could even have weird life going on down there. There could be Venusians down there living, the in the 20s and 30s. I think some of the sci-fi stories and movies and TV things, had people going to Venus and having strange life down there. And probably there was very similar aspects of Venus. Venus is the closest planet to us, most similar in size, a lot of similarities to it. And so there was a lot of interest in trying to go and see what was really down there beneath this. It's the brightest object in the sky after the sun and the moon, very high brightness, and part of that is the reflectivity. I think they say the moon reflects something like 5 or 7% of the light that hits it, we see it as a very bright object in the sky, right? But it's dirty, dark, gray, blackish soil up there. Venus is very reflective. It reflects something like think about 70% of the light that hits it gets reflected back. So that's one reason it's there in the sky. You'll only see it really main in the evening and morning, although it's going around the sun. So with instruments, you can see it wherever the sun is if you can avoid the lights of the sun. The only planet that gets hotter than Mercury is Venus. It's the brightest object in our sky after the sun and the moon. It's rocky like Mercury, but has had its own history that has also had a serious impact on the planet. Some differences between Mercury and Venus. One is Venus still has active volcanism. It has a runaway greenhouse effect, you've probably heard about. Its size, atmosphere is mainly CO2 and sulfuric acid. It gets up to 900 degrees, and that's mainly because of the greenhouse effect. It's the amount of the sun's rays that don't get released back out into the atmosphere. Parts of its atmosphere are fairly similar to ours, but down at the surface, it's very heavy atmosphere, very dense atmosphere, something like 92 times the pressure, atmospheric pressure, than what Earth has at its surface. It's similar to being maybe 3 miles below the ocean surface. The pressure that was there, if you stood up on Venus, you'd be crushed down completely. You couldn't stand up. It would press you down completely. It takes 225 Earth days to orbit the sun, more similar to ours. It rotates against its own orbital direction. I think it's the only planet that does it. I'm not sure. I haven't studied the gaseous ones yet, but it rotates against its orbital direction, which is mainly a braking kind of effect, they believe, because of the atmosphere. So it rotates toward the west. You'd be seeing the sun rise in the west and setting in the east on Venus. It's basically slowed by the drag of its own atmosphere. It takes about 115 Earth days to make one rotation. Okay, so that's a very, very slow time frame too, right? Even longer by almost double than what Mercury's is. So both of these very slow, which has a big impact on temperature. In 1961, Venus became the target of the first interplanetary flight, Venera 1, and it was from Russia and I believe the USSR. They had something about 16 flights. Venera is how you say Venus, I believe, in Russian. And Venera 7 was the first soft landing on another planet. That happened in 1970. So the most important knowledge gained by these Russian probes was that the popular science fiction theories of the time that Venus was able to support life were basically false. The surface conditions were extreme. The atmosphere of Venus supports decks of opaque clouds of sulfuric acid that cover the entire planet. The atmosphere is also in a constant state of vigorous circulation. Winds blow at a speed of 220 miles per hour or more at upper layers, but then only about 6 miles per hour at the surface. It's so heavy that it can't move. There's a region 30 to 40 miles above the surface of the planet that has similar temperatures and pressures as on Earth. So then it's been postulated as a possible area of both exploration and future colonization by humans. There could be life at that place. It would be up in the atmosphere, like 40 miles above the surface. The temperatures and the pressures are similar to Earth's. So if there's something living, it would probably be something floating around up in the atmosphere. The upper cloud layers with more normal temperatures and pressures could be potential sites for microorganisms. There's been some evidence of an unknown UV absorber, something absorbing UV light that they can't really identify yet at that level. It even prompted Carl Sagan, Scott's favorite scientist, in 1963 to hypothesize that a colony of microbes could be absorbing the readily available UV light. More study and exploration is obviously needed. There's been a long-standing debate concerning instruments detecting phosphine at levels conducive to life. Other indications were that the phosphine detection was overestimated or plain wrong. So there's still a lot to find out about this. If there's things that scientists say could be potential life indicators are actual true or not, but they're not sure about it, and more evaluation is needed. So if I go through a few of the 225 Earth days, 115 Earth days for a day. It rotates against its orbital direction. I don't know, what's a battery issue? Its diameter is very close to Earth's, only 400 miles less than Earth's diameter, 521 miles. Most similar to Earth in size, extreme atmospheric and pressure conditions. The atmosphere is 95% CO2 and 92 times the atmospheric pressure of Earth. These probes, the Venera probes that landed, some of them didn't make it to the surface. The original ones were flybys. After Venera 7, they started landing. They had time lapses, time limits of when they were sending material information back that were 21 minutes, 35 minutes, 45 minutes, and then they just click out. They also had some really bad luck with, they had cameras. I think I have a picture to show you about it, but the lenses wouldn't pop off properly. One time a lens popped off and it landed right in a place that didn't allow some good picture taking. So they had a lot of issues with it. Intense temperatures and these active volcanism, runaway greenhouse effect. And they think that it could have been hospitable up to 715 million years ago. That the temperatures might have been, the temperatures were probably very similar, maybe a few degrees cooler even than Earth's temperature. So not that that proves that anything happened there at that time, but it had conditions that were more suitable to life at that time. Today, possibly only in the upper atmosphere, and that is going to take a lot more investigation to see if it's true or not. So scientists' view is that the early environment of Venus was more like that of Earth, with liquid water on the surface. It's known that the sun has increased in luminosity by 25% in the past 3.8 billion years. At some point in the evolution of Venus, greenhouse gas effect went on a runaway path, leading to the current greenhouse dominated atmosphere. No water's been on Venus for the last billion years. The early Earth's Hadean era is very similar to Venus's current state, with roughly 100 times the atmospheric pressure was here on Earth at that time. Atmospheric pressure and heavy CO2 presence and surface temperatures of 400 degrees on Earth. But the plate tectonics that we have on Earth and early photosynthetic life really moderated these really dire constraints on Earth. Venus without a magnetosphere of significant amount and plate tectonics missing, it's much less protected than us lucky Earthlings. So here's a replica of the Venera 1, the first one. Looks kind of 1930-ish or something like that, right? Venera 1 and Venera 2 were intended to fly past Venus without entering orbit. Venera 1 was launched in 1961. Telemetry on the probe failed 7 days after launch on its way to Venus. It's believed to have passed within 62,000 miles of Venus and remains in heliocentric orbit. Venera 2 launched in 1965, but also suffered a telemetry failure after leaving Earth orbit. So this was the developmental time. You can see like an umbrella here, a solar umbrella to protect it, and the probe here. So this was Venera 9, and it actually is the first photo taken from another planet. And you can see part of the probe down here in the rocky soil. They actually meant to take a 360-degree one, but the lens cap on the other side didn't come off. All the way to Venus, and then your lens cap won't come off. And they had that same problem on other ones, but yeah, part of the probe is right here, and this is its landing structure. So it's kind of amazing to think of pictures from so far away. Yes. I don't know if they knew. Yeah, he's asking, did they do anything? How they protected it from sulfuric acid? I mean, I think sulfuric acid is a fairly, I don't know if I want to say benign, but I mean, it wouldn't destroy it in seconds. It probably wasn't their biggest consideration. I'd say the pressure and the temperature are much more of a problem.
Yeah, it only operate for maybe a few hours, but a very short time before it was fried. Yeah.
Right. All these probes, the pressure on Venus at 92 times, it's, it was catastrophic. It was very challenging to its capacity. I think Scott's got a question back there, Joanne. But yeah, they only lasted short amounts of time. They couldn't build, they didn't seem to be able to build one that could last more than an hour and a half or something like that on the planet. And they sent back data and then collapsed. Scott?
Am I remembering correctly that the reason that photograph looks so distorted is because of the refraction through the incredibly thick atmosphere? Was that one of the reasons it looks, the images that you showed just a moment ago is so distorted?
I was assuming, I hadn't heard that. I was assuming it was just the lensing and the structure of the planet. All they wanted to do was maybe see that, but it's a potential possibility. I don't know how atmospheric pressure would affect the camera's lensing kind of thing.
It must have a big fisheye lens.
A fisheye lens, yeah, that's what I'm kind of assuming, that this is the picture I don't know if you'd take this same picture with the same structure back on Earth when they were testing it out. You're hypothesizing that it might have been a flat, nice straight picture, and it's just the high pressures and the conditions on Venus distorted it. I wouldn't think it would either. I wouldn't think it would, but
I don't know if it was Venera 9, but I'm pretty sure one of those probes brought back actual audio, like from the planet, because one of the probes drilled into something that was there, and they were able to get like actual audio from the planet.
I would imagine that that's a obviously achievable task. They're getting audio back from a lot of different probes later, but it might have been the first time that actually we heard the sounds from another planet, huh? Yeah, pretty interesting.
And I might add that sulfuric acid is one of the most incredibly corrosive of all the known acids. So you have to prepare for it. It eats iron, obviously. The lighter metals are just consumed instantly. You have to be prepared. Now, the good part about it is there's no water there, so all you're dealing with is sulfur dioxide and sulfur trioxide. You add water. Right? They don't have water, so they don't have sulfuric acid, but sulfur dioxide and sulfur trioxide are incredibly strong oxidizing agents.
Everybody said they had sulfuric acid in the
The
atmosphere.
clouds were sulfuric acid.
Again, the temperature is, with no water, you cannot have sulfuric acid. It's impossible. you must take sulfur dioxide and put it in water to make sulfurous acid, and sulfur trioxide plus water is sulfuric acid. Take away the water, and you do not have sulfuric acid, by definition.
But before it got hot, there was water on the planet and it evaporated. And so did it create some sulfuric acid before it got super hot? Or did did the water, the oxygen leave the,
It ate up all the metals. If you take sulfuric acid and you add, for instance, iron, you get ferrous sulfate or ferrous sulfide, both of which simply precipitate, and that's where you get iron ore. If you take it with sodium or potassium, it's almost an explosive reaction. If you take it with calcium, it's less. But again, nickel, zinc, iron, nickel, again, cadmium, all of them. It's just eaten alive quickly, very, very quickly.
When
You
say
don't mess with
quickly,
sulfuric acid.
Are you talking hours, days, weeks?
Seconds. You put sulfuric acid and put iron, the iron will be gone within a day. If you put it with sodium, it's gone within seconds, exploding. So
That's why I never build my rockets out of sodium.
yeah, and in the laboratory, we're always
All right, we may
extremely
be getting
careful.
too far into the weeds, but interesting stuff, actually. And it would be interesting. Maybe you can look into that because I did, like John noticed, I said that the clouds are are sulfuric acid, right? And you're disputing that, so we can
Because
both
sulfur
look into that,
dioxide and
and
sulfur
we'll report
trioxide are
back.
gases.
We'll report
They float
back
around the
both.
atmosphere.
Okay. So we will find out more about that. I think, Joanne's got a background in it more than me, so I'm not standing on any Bible saying any of this.
Never argue with a chemist.
Venera 15 and 16 were actually designed to fly around and make a topographic map. So they were able to cut through the atmospheric whatever and the atmospheric clouds. And these are high points and low points. As you get up, you can see it over here, the key. Low points are 3,000 meters below the surface level, up to 7,500 meters above. Pretty large. This is a very high point. Okay. So again, they got some good science and some good things. They're sending back data. Could possibly be audio data and a whole bunch of other stuff too. But they sent back things. They lasted longer up in the atmosphere, up higher than they did when they landed on the planet. This is an artist's rendering, and it's kind of a few interesting things to talk about. It's a very Hadean type of surface there, but they're supposing that you could actually have large areas that people could live in. These could be pods that people could live in, sending down probes near the surface to pick up things that may be useful for them. But living up here where there's less pressure, less temperature, less problems. These probes that landed all on Venus quickly were destroyed, and what I understand by mainly the temperature and the pressure. Temperature's higher than what melt lead.
Yeah, I was just going to add, as I understand it, that layer in the upper atmosphere where the temperature is about, 20 C or so, and the pressure is about 1 atmosphere. At that, as I understand it, at that level, nitrogen and oxygen, like a balloon of nitrogen and oxygen, would be buoyant at an internal pressure of about 1 atmosphere.
Yeah.
So yeah, you could just,
Yeah.
assuming you could build such a structure in a way that's stable enough, then you could live inside that balloon.
Right. Yeah, it could be a free floating kind of stable environment for people.
Okay.
Gravity would affect it, but it would be overcome.
Yeah, surface gravity is yeah. I was gonna say, yeah, the surface gravity is 0.9 something
Right.
G, so it's like just slightly lighter than Earth.
Yeah.
is what you'd feel.
Yeah, so it's such similar size and similar in many ways that basically up at 40 miles, 30, 40 miles up high, you could just have a free living thing, free existing kind of thing that would be buoyant, like you say. So Venus kind of, was very much thought of years and years ago as a place where life could be very similar to Earth's, but been proven pretty much that there'd be much changes. It could possibly be a place that colonists could live at, but under these strictures we just talked about, not on the planet itself. It's a nice picture over there of the Earth. It's a famous picture of the Earth there and ours. We know a lot about the Earth, but I thought I'd go through a few things that show its importance. 365 and a quarter days we know, and 24 hours to rotate around. The tilt of 23 and a half degrees on its axis gives us our seasons that make us have cold and warm, and changes in the weather, has big impact on life on Earth. Diameter 7,918 miles. Obviously suitable for life. Protective magnetosphere is a big aspect of what made our planet able to withstand the solar winds and the problems that have come in, the challenges that come in from space. Liquid water and oxygen are prevalent. It has a protective atmosphere, much larger than any of the other rocky planets. And the big change of tectonic plates and continental drift, all that has created something that's been very important for life to develop on Earth as well, too. Its metallic core is only about 17%, but that creates the magnetosphere, makes us into a big magnet that creates waves that go out into space and stop the solar wind from impacting us. Challenges of that.
I may have missed it. What was the significance of plate tectonics to life?
To life? Well, I would say that because it kind of stirs the soup and it makes things different in different places, it evaluates, it impacts what lives and what dies. Yeah, I would say that also just the whole, if you look at the whole Atlantic Ocean, it's none of the rocks in there are older than 200 million years old, which is not long geologically, right? That whole length has been upwelled, bringing in new carbon, new material into the earth, spreading out, spreading things away apart. And so that has a big impact on new nutrients being brought into the system.
Well, one of the things I was going to say, as I understand it, and this is outside my area of expertise, so I'm not sure, but that at least it's, I don't know how much this is hypothesized versus like definitely true, but that like all the volcanic activity and all released a lot of gases to give us our thick atmosphere, including releasing a lot of the oxygen and water vapor that makes up the oceans and the
Right.
very water-rich and oxygen-rich atmosphere.
Yeah, I think Joanne was talking once about how the rocks hold most of the oxygen, most of the water on the planet, and that this recapitulation of this just puts out fresh materials, fresh life materials. Mm-hmm. Yeah, no, definitely. Mm-hmm. Right. Yeah, I think that a lot of the I mean, you could imagine that life could develop. Life wasn't dependent upon the fact that there was continental drift and tectonic plates, but it added a lot of value in terms of new nutrients, and it had a big impact on how life developed on our planet, right? And the impacts it's had. Scott in the back. That's not a prominent theory about the
Yeah.
origin of life.
One
Somebody
of the
turned off the microphone?
right. One of the one of the prominent theories about the origin of life is that it originated from chemical vents in the ocean floor, and that would not be possible if our crusts weren't thin enough that lava and hot minerals could boil up. So the thin dynamic crust created the conditions that may have been necessary for the origin of life itself.
I think you're right. Yeah. All good points. Yeah. So here's getting to that. Here's some core comparisons. If you look at Mercury's core, so much an outer molten core and a solid inner core, and so little mantle and crust on it. Very high in metallics and very low in silicates and different things that make the lithosphere, make the rocks. Earth's core and Venus, more like this. This is obviously showing Earth's core, mantle taking up a lot, outer core, inner core. So just some level of comparison of that. Yes.
So if Earth and Mercury both have this metal core, why does Earth have a magnetosphere and Mercury doesn't?
Have a what sphere?
Magnetosphere? Earth has a magnetosphere, and
Oh,
you
yeah.
said that Mercury doesn't really have a significant one.
It has to do with the fluidity of the core. If the core isn't fluid, it becomes what they call a dead planet. It doesn't move around like a motor has to move around to create electricity.
Okay, so
And
liquid metal has to.
What's that?
You need liquid metal then?
Yeah.
Core? Okay.
The speed of rotation.
Yeah, the Earth's rotation is relatively fast compared to Mercury's. So, right, just electrodynamics. Moving charge creates a magnetic field, right? So the thing swirling is what's creating that.
Right. Right. Well, we'll probably. I just want to point out a couple things about Mars, the last of the rocky planets. But if you look on here, the thing that really jumps out, two things that really jump out. One are the size of these big shield volcanoes. This is when you think of, you don't see the points of Mount Everest showing up on Earth, right? But you see these things on Mars, which is smaller. A smaller it's only 53% of the Earth's diameter, so it's a much smaller planet. But still, these things are about twice as tall, I believe, as Mount Everest, even though they're on a much smaller planet. So the Olympus Mons, 13.6 miles high. Amazing. And then the other thing that's been found, one of the Mariner probes found this large rift in here. We have a great rift where there's movement of our plates and so on Earth. But this thing, if you compare it to the Grand Canyon, this thing is 125 miles wide and it's 6 miles deep. The Grand Canyon is about a mile deep, right? Just amazing, amazing structures on
Mike,
here.
it looks like we're running over time.
Say what?
Looks like we're running over time.
Yeah, I think all we'll do is I just wanted to talk about those two things, and we'll cover up more of these. I'll talk some more about planets in a couple weeks. But anytime, any questions or thoughts that you'd like to say, more than welcome to take them right now. But I think it's like 70% or something like that. quarter of
So it's about 25.
25%.
So what would that be equivalent to altitude?
In space.
Okay.
Yeah. The effective, like you can't stand at the radius of low Earth orbit, but if you could, it would be like 60% of surface gravity. So like you'd have to be miles, like well out past the surface of the Earth before you get down to that.
No way you survive on Mars without what?
Pressurized suit.
Yeah.
Suit.
Do we know if Venus has tectonic shift activity and stuff like that?
It has more. It doesn't really have plates like we know that, at least as far as we can tell now. But it has volcanism yet, and I think there's a lot more to find out about what's really going on under the crust. It is a similar crust and mantle layer and so on to Earth's. So you could speculate that it has some level of it, but not well known at all by us. Okay. All right. Well, thanks so much for coming in. Appreciate it. Appreciate
Mike.
all the help too. This is a tough topic, and knowledgeable people are always great to have here when we talk about this stuff.
It's
So,
a wonderfully eclectic group, isn't it?
what's that?
It's a wonderfully eclectic group.
Oh yeah, yeah. It makes you feel comfortable coming in, talking, knowing that people will, add the value to what you're saying. So, thanks so much. Appreciate it very much, and we'll talk some.